Continuing with our discussion of the weight-volume relationships, as I mentioned before, G sub s is the specific gravity of the solids, a typical number 3.0 or 2.7 for a typical soil particle. Again, remember the specific gravity refers to how many times greater is the density of a single particle compared to the density of water. So, like I say, a rock, typical rock, has about three times the density of water. And that is the gamma of the solids, density of the solids, divided by the density of water. And once more, gamma is weight over volume, gamma d is weight of the solids over the volume, and gamma s is weight of the solids over volume of the solids. Okay, so I'm going to verify these equations, or one of the equations anyway. We'll start with the equation S times E is equal to G sub S times W. We're just going to substitute S is what? Volume of water over volume of the voids. E is void ratio, volume of voids over volume of the solids. And just canceling, we get V sub W over V sub S. G sub S we know is gamma S over gamma W. Gamma S is weight of the solids over volume of the solids. Gamma W, weight of the water over volume of the water. And so when we, so in our equation, I'm going to take S times E divided by G sub S. And what do I get? S times E, just by substitution. Volume of water over volume of the solids there. Let's go back here. S times E is volume of water over volume of the solids. That's that. And the G sub S is weight of the solids over volume of the solids divided by that. So this term represents G sub S in the denominator. And you can see there's a lot of cancellation. We get weight of the water over weight of the solids, which is small w, which is water content. So I get that S times E over G sub S is equal to W, which is that equation. So that verifies that equation. I'm just going to give you equation 2 and 3. Do the same sort of thing. Just make substitutions and you'll get a lot of cancellation, and just do those at home. Okay, I want to do another example. It's going to be this. It says find gamma, E, small w, and S for a chunk of moist clay that weighs 45 pounds, has a volume of 0.43 cubic feet, and when dried, the soil weighs 40 pounds, and the G sub S of the particles is 2.67. We can draw a little picture of it. So in other words, here's a little picture. What are we saying? Well, we're saying that the weight of the solids is 40 pounds. Well, now we're solving it here. This is the solution. We're saying that the weight of the solids is 40 pounds. How do I know the weight of the solids is 40 pounds? Because when dried, it weighs 40 pounds. So that's the weight of the solids. Now, how can I get the weight of the water? Well, if it weighs 45 pounds, when it's moist, and 40 pounds when it's dried, well, the weight of the water is simply going to be 45 minus 40, which is 5 pounds. So I've got the weight of the solids, I've got the weight of the water. I've been given that the total volume here of this whole box is 0.43 cubic feet. And that tells me that the density, gamma, So I'm going to tick these off. Gamma, for instance, is what? Is weight over volume. 45 pounds over the volume, 104.6 pounds per cubic feet. And we've already said that the weight of the solids is 40 pounds. And we know that gamma W, we're in English units, so it's going to be 62.4 pounds per cubic feet. You need to know that one. And so we can get the volume. Our goal is to get the volume of the water at one point, or not our goal, but we need to get that along the way. And how do I get that? Well, I know that the density of water is weight of the water over volume of the water. Well, I know the volume of the, or the weight of the water, so I can solve for the volume of the water. And just solving this equation, then I get, what, 62.4 is equal to 5 over volume of the water. I solve for the volume of the water, I get 0.0801 cubic feet. Now, I just want to emphasize one thing. For all the problems that you will do, if you know the weight of the water, you can get the volume of the water. Why? Because I know the density of the water. So, in all cases, if you know the weight of the water, you can get the volume of the water. Similarly, we're going to find in reverse, if I know the volume of the water, I'm going to be able to get the weight of the water. Why? Because, again, I know the density of water. So, the density, like I say, these are weight and volume problems. And so what it comes down to, again, if you know all the weights and all the volumes, you can solve any problem that I give you. So a lot of times that's what you do. You just go for all the weights and volumes you can. And so the density is important. Density is the thing that's going to bridge us or get us from weight to volume or volume to weight. So if I know the density, I'm going to be able to go between the weights and volumes. So that in this particular case, notice, here's a density that I know. In other words, I know gamma S. Why do I know gamma S? Because we've been given that G sub S is 2.67. And we know that G sub S times the gamma W is my gamma S. So I want to get the gamma S. It's so 2.6 times 2.67 times 62.4, 166 pounds per cubic foot. What does that mean? That's gamma S is the density of the solid particles, and that tells me what? If I know the weight of the solid particles, I know the volume of the solid particles because I know the density. So I do know, in this particular case, I know the weight of the solid particles is 40 pounds. So since I know the density of the solid particles, I can get the volume of the solid particles. So the volume of the solid particles is W sub S over gamma sub S. It's 0.241 cubic feet. That means I can get the volume of the voids. Why? Because it's simply the total volume minus the volume of the solids. Anything that's not solids is a void. So I've got the volume of the solids. I've been given the total volume. The total volume has been given to be 0.43 cubic feet. And so I can get the volume of the voids by subtracting them. It's 0.189 cubic feet. And now I can solve for, I know I have weights and volumes, so I go to my basic definitions. Void ratio E is volume of the voids over volume of the solids. Well, I know what those are. I know the volume of the voids. I know the volume of the solids. So I get 0.79. The water content is weight of the water over weight of the solids. Well, I've got the weight of the solids. I got the weight of the water. Gives me the water content, 0.12. And S is what? It's the volume of the water over volume of the voids. There's the volume of the voids, and I figured out the volume of the water. So, like I say, once I know all those weights and volumes, I can solve for any of the things that I ask you for, you can solve for when you know all the weights and all the volumes. Now, a lot of times these are put in percentages. So instead of saying that the degree of saturation is 0.42, we say it's 42%. Water content is not a real percentage, but for some reason we frequently put it in a percentage, and instead of 0.12, we'll say the water content is 12%. Water content is not a real percent. Why do I say that? Because in rare cases, the weight of the water can be greater than the weight of the solids, which means that the water content can be greater than 100%. So it's not a real percentage. Is all you can see. It's not a real percentage, but for some reason, just by tradition, water content is frequently expressed in percentage. Let me just say, since I've indicated here, that one of the things that we find is that clay particles and silt particles are not like sand and gravel particles. Sand and gravel particles are like little rocks. That's an easy way. I just want you to know, and we'll talk more about this when it becomes more important, that clay particles are more like flakes. So I want you to think of clay particles as flakes, like tiny corn flakes or tiny potato chips. And they tend to be rubbery. So I want you to think of them as rubber, actual clay particle like a rubber potato chip or a rubber corn flake. But very tiny, obviously. So it ends up to be very important. They're flaky and they're rubbery and they bend and they flex. They're not like little rocks. Gravel particles are little rocks. They're hard. They don't bend. Sand particles are basically little rocks. They don't bend. They don't do any of that. So, okay. Another problem. Example. Calculate the void ratio and specific gravity for a saturated soil with a unit weight or density, gamma, sometimes I'll say unit weight, sometimes I'll say density, same thing, of 117 pounds per cubic foot and a water content of 41%. Okay. Now, we can, for instance, hold on, let me, okay, yeah. I said that you're supposed to solve this at home. That's what I thought here. So, whoops. And I've solved. I'm going to solve that for you, I guess. So no, I'll just show it to you. You can solve this. So this is we decided we could get two equations, two unknowns, and so when I plug these in, I get so I'm going to use this equation, I get that. I'm going to use this equation, I get that. I got the two equations, two unknowns, and now that I plug them in, I can solve them. I get that answer, so I'm going to go on to the next. I'm going to do this same problem now, but I'm going to do it the more fundamental way. In other words, I've shown you how to solve this problem with the shortcut equation. So here are these are my shortcut equations. You can solve problems with the shortcut equations, but if you there's another way to solve those problems and get all the weights and volumes. So how do you do it finding all the weights and volumes? So I'm going to do the same problem, but I'm going to use the fundamental equations. So notice, one thing I want you to note in this problem is that no weight or volume of any sort is specified. So in other words, I read this problem, and what do I see? I've been given a density, I've been given the degree of saturation, because it's saturated soil, and I've been given a water content. I have not been given a single weight, and I have not been given a single volume. None. Okay, so that means that I can make an assumption. In other words, actually, I have to make an assumption if I want to use my fundamental equations. Is to use the fundamental equations, we need to assume a weight or a volume. Now, like I say, you got to be careful in assuming a weight or a volume in any of these problems, because you have to make sure that no weight or volume of any sort is specified. If any weight or any volume is specified in the problem, you cannot make an assumption of what the weight or volume is. But in this case, no weight or volume is given. I can make an assumption. So I'm going to assume that we have 1 cubic foot. And so I assume a volume. I can only assume one thing here. So don't assume multiple things. I can assume a weight or a volume. In this case, I'm taking the volume as 1 cubic foot. And what does that mean? I can conclude then I have 117 pounds. Why? Because my density is 117 pounds per cubic foot. So, okay. So I now have capital W, the weight, 117 pounds. Now, I'm going to show you a little trick here, and this is what you need to know. The trick is know this. When we have capital W, so when we have capital W and small w, in other words, we have the weight and we have the water content, then what we're going to find is that we get 2 equations, 2 unknowns. Now, how does that work? Well, the capital W is weight of the water. The total weight is weight of the water plus weight of the solids. Small w is weight of the water over the weight of the solids. So we have these 2 things. So for this particular problem, I've got the total weight is 117. That's weight of the water plus weight of the solids. Weight of the water plus the weight of the solids. And the water content is weight of the water over the weight of the solids. So I have the 2 equations. My 2 unknowns are weight of the water and weight of the solids. How do I solve that? It's quite simple. I use the bottom equation first here in this particular case. So the weight of the water is 0.41 times the weight of the solids. I substitute that into the first equation. So I put it up into here. So I get 117 is 0.41 Ws plus Ws. And I get the weight of the solids is 117 over 1 plus 0.41. I get 83 pounds. For the weight of the solids, how do I get the weight of the water? I simply subtract the total weight minus the weight of the solids gives me the weight of the water. So I get the weight of the solids is 83 pounds. I get the weight of the water is 34 pounds. Again, if I know the weight of the water, I know the volume of the water. Why? Because I know the density of the water. So the volume of the water is the weight over the density. So now I have the volume of the water. So again, I'm just trying to get weights and volumes. So I'm doing pretty well. I've got the weight of the solids, the weight of the water, the volume of the water. And now what else can I get? Well, the soil is saturated, so that means what? That means the volume of the water is equal to the volume of the voids. So I know the volume of the water, and so that means the volume of the voids is 0.54, is the same as the volume of the water. And so the volume of the solids is the volume minus the volume of the voids. I've assumed the volume is 1 cubic foot, so I now can get the volume of solids by that subtraction, and that gives me the volume of solids of 0.46. And so now I have my weights and volumes, basically. So I've got void ratios, volume of the voids over the volume of the solids. I do that. My specific gravity is gamma S over gamma W, which again is weight solids over volume of solids over gamma W. So I get the G sub S, and there's my G sub S. Those are the two things that I needed to get. So, two ways to work this problem. One way is to use the shortcut equations. Here, get two equations, two unknowns. If you know your shortcut equations, you can do that. Otherwise, you have to go back. You have to go to the basics and get weights and volumes. Most of the time, the shortcut equations are faster and simpler. And that's why the shortcut equations are helpful. But if not, you can go to the basic equations, get your weights and volumes. I'm going to show you another trick. So let me just go back to, this is the trick you need to know. It says, when we have big W and small w, we get two equations, two unknowns. That's really handy to know, because you're going to use that a lot. So if you see that in the problem the total weight is given and the water content is given, you should just immediately think two equations, two unknowns. Let me solve this really quickly, and I'm going to get some very fundamental information, and that's step one. I'm going to give you another one. If they're given the volume and the void ratio, then again we have two equations, two unknowns. How does that work? Well, let's take this example. A soil has a volume of 30 cubic meters and a void ratio of 0.75. What are the volume of the voids and volume of the solids? Okay, well, what do I know? The total volume is volume of the voids plus the volume of the solids. Void ratio is volume of the voids over the volume of the solids. That gives me two equations, two unknowns. Why? Because I get 30 is volume of the voids plus volume of the solids. 0.75 is volume of the voids over the volume of the solids. I simply, again, I work with this equation here at the bottom. I get volume of the voids is 0.75 times volume of the solids. I then substitute that into that. I get that equation, and then I simply solve for V sub S. Gives me that. By subtraction, I get the volume of the voids and volume of the solids. So the next trick you need to know this trick. Again, if I give you on a problem capital V and E, you should look for these things. And once you see them, it's going to give you the ability to start solving. Okay, I'm going to let you solve this problem here. A soil with a water content of 15% has a unit weight of this, GS of 2.8, find E and S. So why don't you pause the video and solve this problem. Write it out and do what you can to solve it. Okay, I'm going to assume that you've paused the video and solve this. Actually, let me also give this one to you. Soil has a water content of 21%. It weighs 100 pounds. G sub S is this. Find the weight of the water, weight of the solids, volume of water, and volume of the solids. Okay, so why don't you pause the video and work both of these problems? I guess probably works better. Okay, I'm going to assume that you've solved both of these. I'll just go over them. Okay, so so it's a good idea to write down what is given. The water content is 15%, right? Small w is 0.15. It has a unit weight of 19. Gamma is 19 kilonewtons per cubic meter. The G sub s is 2.8. We write G sub s equals 2.8. And then I'm asking you to find void ratio and degree of saturation, so I write E equals question mark, S equals question mark. That just gives you a feel for, so you're not starting out blindly. Okay, you can look for my shortcuts. Am I given capital W and small w? I'm given small w, but I'm not given capital W, so I can't use that. Am I given capital V and E? No, I'm not given those two. So I don't have those two equations, two unknown. So let's look at my shortcut equations, for instance. Here are my shortcut equations. You can write them down, or two of them that might be helpful. And what else do I know? I know that. I know that gamma is equal to gamma d times 1 plus w. So what do I see? If I look at this equation, what you look at your shortcut equations, well, I know gamma. I know water content, so I can get my gamma d. So I only have one unknown, so I solve for my gamma d. 19 over 1, I get that for my gamma d. Then what do I know? Then I know that gamma d is equal to, from this expression, putting in s equals 0, I get gamma d is equal to g sub s gamma w over 1 plus e. And what do I see? I see that the only thing missing from this expression is e. So I plug everything else in, and I get my e. That's that one. And then I know that the other shortcut equation is s times e equals g sub s times w. And I solve for s. Let's plug everything in. It's just a plug-in. So this is one that gets us through using the shortcut equations. Let's look at the bottom one. So it says that the soil has a water content of 21%. Small w is 0.21. It weighs 100 pounds. Big W is 100 pounds. G sub s is 2.4. I write that down. And then I'm trying to find these quantities. Just write that out. So that gets me started on the solution, so I can see what's using the notation. And okay, now in this particular case, what do I know? I've got big W and small w. That should lead immediately to two equations, two unknowns. Equation 1, equation 2. I'm not going to go through it. You can see it. I solve for it. I get that the weight of the solids is that, the weight of the water is that. And then I now have solved the first two. So, and then, what do I know? Well, I know gamma W. Again, if I know the weight of the water, I know the volume of the water. How do I know that? Using the density. So I use the density, I get the volume of the water. And then since I have the specific gravity, I also know the density of the solid particles. Since I know the weight of the solid particles and the density of the solid particles, I can get the volume of the solid particles. So again, I just use the density. Note that the density is what? GS times gamma W. That's the density of the solid particles. And I get the volume of the solid particles. Okay, we'll stop there.